Hello my dear students. Today we will talk about the law of levers, and this lesson is for grade 6 unit 1 lesson 2. We have learned in the previous lesson that any lever is a rigid bar that rotates around fixed point called fulcrum, and it's affected by two forces, which are the effort force and the resistance force. According to the type of lever, sometimes the effort force is smaller than the resistance force, and sometimes the effort force is more than the resistance force, and sometimes the effort force is equal to the resistance force. The mathematical equation that explains the relation between effort force and resistance force is called law of levers. Before we talk about the law of levers, we should know two important definitions. The first one is the effort force arm. What is the meaning of effort force arm? It's the distance between the effort force and the fulcrum. Again, the effort force arm, it's the distance between the effort force and the fulcrum. And the second definition is the resistance arm, and it's the distance between the resistance and the fulcrum. The resistance arm is the distance between the resistance and the fulcrum. So, the effort force arm, the distance between effort and fulcrum. The resistance arm is the distance between resistance and fulcrum. What about the law of levers? The law of levers, it's a mathematical equation that explains the relation between effort force and resistance force, and states that the effort force times its arm equal the resistance force times its arm. Again, the effort force times its arm equal to the resistance force times its arm, where the effort force or the resistance is inversely proportional to its arm. Again, the effort force and the resistance is inversely proportional to its arm. The effort force and its arm is inversely proportional. Inversely proportional means that by increasing effort, the arm decreases, and by decreasing the effort, the arm increases. It means that they are opposite to each other. And also the resistance and its arm. By increasing resistance, the arm decreases, and by decreasing resistance, the arm increases. So that when the force arm and the resistance arm are equal, the effect force equals the resistance force. When the effort arm and the resistance arm are equal, so the effort equals resistance. And we say that this lever doesn't conserve effort, doesn't save effort. When the effort is equal to the resistance, this lever doesn't conserve effort. Number 2, when the force arm is longer than the resistance arm, so the resistance force is larger than the effort force. The resistance force is larger than the effort force. And this lever conserve effort. This lever save effort. Number 3, when the resistance arm is longer than the effort arm, the effort force is larger than the resistance force. So this lever doesn't conserve effort, doesn't save effort. Why? Because the effort is more than the resistance. So we can say that the lever conserves effort when the resistance is more than the effort. When the resistance force is more than the effort force. It means that the effort done for something which have a great resistance is very small. Again, the effort done to make something with a very large resistance is very small. So the lever conserve effort. And when does this case occur? This case occurs when the force arm is longer than the resistance arm. So the resistance is more than the effort force. And this lever conserve effort. So I have here two cases in which the lever doesn't conserve effort: when the force arm and the resistance arm are equal, and when the resistance arm is longer than the effort arm. And the only case in which the lever conserve effort is when the force arm longer than the resistance arm. So the resistance is larger than the effort, and this lever conserve effort. Give reason. When the resistance arm is longer than the effort arm, the effort force is larger than the resistance. Why? Because the effort force or resistance force is inversely proportional to its arm to verify the balance in the lever to achieve the law of levers. There are some important notes. The first one, the effort force or resistance force are measured by unit called Newton, like weight. The effort force and the resistance force are measured by Newton. The distance between the effort force or the distance between the resistance force that we call them effort arm and resistance arm are measured by meter or centimeter as they are distance. So they are measured by meter or centimeter. The factors that determine the values of force and resistance are the force arm and the resistance arm. We can determine the value of force and resistance by knowing the force arm and the resistance arm. So here the effort or resistance are measured by Newton. The force arm and the resistance arm are measured by meter or centimeter. And the factors that determine the values of force and resistance are the force arm and the resistance arm. Let's see here an example. Complete the following table where the value of force and resistance are expressed by number of coins. Here, the effort force, the number of coins are 2, the effort arm 5 centimeter, the resistance number of coins 1, the resistance arm is A. And how can we get A? By applying the law of levers. The law of levers states that the effort force multiply its arm equal resistance force multiply its arm. So A equals 2 multiply 5 divided by 1. So A equals 10. And so on in B, C, and D. Example number 2. Calculate the force that the boy exerts to maintain the balance of seesaw where force of girl equals 400 Newton, where the force arm of a boy equals 2 meters and the force arm of a girl equals 1.5 meters. And is this lever conserve effort or not? The answer here, by applying the law of levers, effort times its arm equal resistance times its arm. Here I have the effort is 400 times 1.5, which is the effort arm, equals the resistance, which are unknown, multiplied 2. So here 400 times 1.5 divided by 2 equals 300 Newton. So the resistance equal 300 Newton. By knowing that the resistance equals 300 Newton and the effort equals 400 Newton, so here I have the effort more than resistance. And in this case, this lever doesn't conserve effort. Why? Because the effort force is larger than the resistance. Example number 3. In the following figures, determine by drawing the position where only one weight equals 1 Newton is placed to regain the balance of the lever. Keeping in your mind that the distance between every two openings is 1 centimeter. I have here resistance equal 1 Newton. Effort force equals 1 Newton also. The arm of resistance is 2 centimeter and he wants to know the arm of force, the arm of effort force. So 2 multiply 1 divided by 1 equals 2 centimeter. In this case, I have the resistance equal 2 Newton, the effort force equal 1 Newton, the arm of resistance equal 2 centimeters, and he wants to know also the arm of force, so 2 times 2 divided by 1 equals 4 centimeters. So here the weight must be placed away from the fulcrum by 4 centimeters. Now we will talk about the law of levers and conservation of effort. The relation between the type of lever and its ability to conserve effort. Let's remember the 3 types of lever. We said that there are 3 types of levers: first class levers, second class levers, and third class levers. In the first class levers, I have the fulcrum between resistance and effort. In the second class lever, I have the resistance between fulcrum and effort. And in the third class lever, I have the effort between resistance and fulcrum. By applying the law of levers on the three types of levers, we find that in the first class levers, there are three possibilities in this type of levers, which are: the first possibility is that the arm of effort is shorter than the arm of resistance, and this happened like in the following drawing. Here, the effort force is larger than the resistance force. Why? Because the arm of effort is shorter than the arm of resistance. So, the first class lever in this possibility doesn't conserve effort or has a mechanical benefit. Why? Because the effort is larger than the resistance. So we can say in this case of the first class levers that this lever conserve effort. The second possibility is that the arm of effort is equal to the arm of resistance. In this case, the effort force is equal to the resistance force, and in this case also the first class lever doesn't conserve effort or has no mechanical benefit. Why? Because the effort is equal to the resistance. The third possibility is that the effort force arm is longer than the resistance arm, and as the effort arm is longer than the resistance arm, so the effort force is smaller than the resistance. And in this case of the first class levers, we can say that this case of the levers conserve effort and has a mechanical benefit. Why? Because the effort is smaller than resistance. So the first class lever in this case only conserve effort. When does the first class lever conserve effort? It conserves effort when the effort force arm is longer than the resistance arm, as in the crowbar. In this case, the effort force is smaller than the resistance force. Generally, some of the first class levers conserve effort, but the others don't. Okay? Let's see the second class levers. In the second class levers, we have the resistance between effort and fulcrum. Let's see here the arm of resistance and the arm of effort. I have here the fulcrum, and I have here resistance, and I have here effort force. The effort arm, here, the distance between effort and fulcrum. The resistance arm is the distance between resistance and fulcrum. So, in the second class levers, always the effort arm is longer than the resistance arm. So the effort force is always smaller than the resistance force. So the second class lever always conserve effort. Why? Because the effort arm is always longer than the resistance arm, so the effort force is always smaller than resistance. What about the third class levers? In the third class levers, I have the effort force between resistance and fulcrum. So here, the effort arm is shorter than the resistance arm. So in the third class lever, the arm of resistance is always longer than the arm of effort force, so the effort force is always larger than resistance. So the third class levers has no mechanical benefit. Why? Because the arm of resistance is always longer than the arm of effort, so the effort force is always larger than the resistance. What is the importance of the third class levers? The third class lever, the sum of the first class lever that do not save effort, are beneficial in other things. Let's remember the importance of levers. We said that it's used to increase speed, increase force, increase distance, avoid dangers, accuracy and performance. We have different importances. If the lever doesn't conserve effort, if the lever doesn't increase force, it can increase speed, it can increase distance, it can avoid danger, it can help me to perform some functions in an accurate way. It allows us in many other importances other than increasing force. So, the third class levers and some of the first class levers that do not save effort have other benefits. Like what? Increasing distance, increasing speed, avoid dangers, and accuracy and performance. So, let's have here a comparison between the three types of the levers. In the first class lever, I have the fulcrum between effort and resistance. In the first class lever, the forced arm may be longer, shorter, or equal to the resistance arm. Some of the first class levers save effort. The benefits of them: some of them have mechanical benefit, but others have other benefits like increasing speed or distance. Like what? Like seesaw, scissors, balance, pliers, and suction pump or water pump. In the second class lever, I have the resistance between fulcrum and effort. The force arm is always longer than the resistance arm. The second class lever always save effort, and all of them have benefit. Like what? Like the nutcracker, wheelbarrow, and bottle opener. The third class lever, I have the force or the effort force between resistance and fulcrum. The resistance arm is always shorter than the effort force arm. About saving effort, it doesn't save effort. The benefits, they are used to increase speed and distance, and also used to avoid dangers like tweezers, hockey pad, ice holder, and manual broom. So in this lesson, we talked about the law of levers and conservation of effort, and we classify the types of levers according to their ability to conserve effort. We said that the law of levers states that effort times its arm equal resistance times its arm. And the first class lever sometimes conserve effort, the second class lever always conserve effort, and the third class lever always doesn't conserve effort. That's all for this lesson about the law of levers and conservation of effort. I hope you enjoyed it. If you have any questions, leave it in the comments and I will answer it immediately. Stay home, stay safe, and good luck.